Hi, Chem 201. We're going to go ahead and continue our lecture for Chapter 1, which is a review of topics in general chemistry that are going to be critical for you to know and understand in order to succeed in organic chemistry. So let's go ahead and continue where we left off before. So this is the second lecture, the continuation of the lecture 1, Chapter 1. So this would be the lecture 2 for Chapter 1. Okay. Okay, so the next topic on our agenda is going to be molecular geometry. And again, these topics that I am describing, there are individual lectures in the review of general chemistry folder in the week 1 module that actually goes into slightly more detail in case you need to brush up on any one particular subject. So remember that the chemical reactivity of molecules depends on the three-dimensional structure of the molecules as well as the nature of the bonds between atoms. Structure actually is equal to function. So if you guys take biochemistry, you're going to find out that the three-dimensional structure of proteins and the three-dimensional structure of ligands that bind to those proteins that actually induce all kinds of chemical reactions are dependent on their fit, which is a factor of their three-dimensional structure. So we have to know something about how to predict a three-dimensional structure for a molecule. This is called molecular geometry. This describes the position of the atoms in a molecule relative to one another. Here I have a ball and stick type of a model. This is what you're going to do if you get the organic chemistry molecular model set that I gave you, or that I require you to get for this class. You're going to be able to draw models and they're going to look like this. This is space filling. And this just gives you an idea of the relative size of the actual atomic orbitals. So carbon's a lot larger than hydrogen. So you can see this black part is a lot larger than any one of those individual hydrogen atoms there. This is by far more useful to us. And when you get your molecular modeling kit, you should be building molecules as we go along, because one of the skills here is sort of being able to picture things in three-dimensional space. And if you build models of things, that helps you be able to picture them in 3 dimensions a lot easier than if you're just looking and trying to visualize them from a 2-dimensional piece of paper. So we know that there's various geometries that molecules can adopt based on valence shell electron pair repulsion theory. If I have two charge groups, right? If I have 2 electron groups, I can be linear. If I have 3 electron groups, I can be trigonal planar. 4 electron groups gives me a tetrahedral geometry. 5 electron groups gives me trigonal bipyramidal geometry. And 6 electron groups can give me octahedral electron geometry. Now, this part here was done in Chem 121, which is Gen Chem 1. If you took the other prerequisites, you may not have gone any farther than tetrahedral. The good thing is, those are the geometries that we really have to know. I basically only care about linear, trigonal planar, and tetrahedral. Those geometries are the geometries of carbon compounds. So those are the geometries that we're actually going to focus on in this course. So just as a review, valence shell electron pair repulsion theory is based on 2 concepts. Atoms are surrounded by regions of electron density, or electron groups. Those are synonymous terms. And these regions of electron density repel each other because electrons are negatively charged. So areas of negatively charged electrons are going to repel other areas of negatively charged electrons. So again, this chart gives us the geometry that we need to know. And remember, I have electron geometry right? And that's going to be dictated here by the number of groups. But I also have molecular geometry. And really, I only care about these molecular geometries. So this is going to be trigonal pyramidal. The electron geometry is tetrahedral, but the molecular geometry is trigonal pyramidal. And then this is going to be bent, right, like water. And then the molecular geometry here is just tetrahedral. So remember, the electron geometry is equal to the molecular geometry if I have no lone pairs. If I have lone pair, like in the ammonia or in the water, then what I'm doing is sort of the electron geometry, the number of charge clouds actually determines the three-dimensional space, but those lone pair aren't really counted in what the shape of the atoms, in the actual shape of the atoms, which is considered to be the shape of the molecule. Remember, lone pair are especially repulsive, right? They have a high repulsion force with other areas of electron density because they're localized on a single atom instead of shared between two nuclei like in a bonding pair. They have a larger repulsion with other electron groups. So they can collapse these bond angles. Remember, my tetrahedral bond angle is 109.5. This is going to be about 107. And this is going to be about 104 because those lone pair have an extra repulsion to them and sort of collapse the bond angles. Here, you're going to look at other examples where this is trigonal planar here, and then linear molecules. So this is it. We learned a lot about valence shell electron pair repulsion, but what you actually need to know is right here on this slide, because these geometries are the geometries that carbon makes. In particular, if I have a carbon with 4 single bonds, I'm tetrahedral. If I have a carbon with a double and 2 single bonds, I have trigonal planar geometry. And if I have a carbon with 2 double bonds or with a triple bond and a single, oops, I don't want to make that a hydrogen. I want to make that sort of generic. That is going to give me that linear geometry. So again, I really care about what hydrogen does. I mean, what carbon does. So these are the geometries that carbon does. So we focus on these. Remember, the electron domain geometry or the electron geometry is the arrangement that includes both the bonding and the non-bonding electron pairs around the central atom. Molecular geometry is the shape that those bonded atoms take if I just sort of connect the dots between atoms and I sort of ignore the lone pairs. This distinction is very important. Remember, electron geometry is including all of the groups, and that's going to actually define the basic geometry of the molecule. But when I consider what the molecular geometry is, I'm just looking at the shape that the atoms make. So very important distinction. Remember, when I look at methane, ammonia, and water, I have CH4, I have NH3, and I have H2O. So CH4 is going to have 4 electron groups, and I'm going to have a tetrahedral geometry. Since those hydrogens are all the same, my bond angle is going to be ideal at 104.5. Again, when I have nitrogen, I have 3 bonded atoms, and I have the lone pair. The lone pair is actually going to collapse this bond angle a little bit because it has a larger repulsive force with the other electron bonded to the hydrogens, and it's going to take up a little more space. Same thing with water. If I look at the water molecule and I have those 2 lone pairs, again, my tetrahedral electron geometry, those bond angles between the actual atoms is going to be a little bit, well, 3 degrees in this kind of a molecule is a lot. It's going to be a lot more collapsed. But again, my geometry of the molecule is actually, if I look at sort of what shape they make without the lone pair. So again, this will be trigonal pyramidal, and this will be bent. All 3 of these molecules have a tetrahedral electron geometry, but for ammonia, I have a trigonal pyramidal molecular geometry, and for water, I have bent. So here, I'm looking at trigonal planar geometry, right? This would be CH2O, which is a formaldehyde. Again, I have 3 areas of electron density, so that gives me 3 bonded group, no lone pair, which gives me a trigonal planar geometry. All of the atoms are in the same plane. Notice this is just a little bit larger than what I would expect. 120, your typical geometry is going to be 120 degrees. And that's because atoms actually take space, and some atoms are larger than other. The oxygen is larger than the hydrogen, so it probably requires a little bit more space. But in these situations, I'm really just sort of, I don't really have to know that those angles are, you wouldn't know those experimentally. You could, unless they're experimentally determined, and you can just sort of assess, well, the carbon's larger than the hydrogen, so it's going to take a little bit more space, which will make this bond angle a little bit lower. And then this oxygen is larger than carbon, or larger than the hydrogen, so it's also going to have an angle there, which is a little bit lower than 120 degrees, because this part is actually taking more space than if it was another hydrogen. If it was another hydrogen, something equivalent, then that would be the ideal bond angle of 120 degrees. Remember carbon dioxide, acetylene, right? My central atom is here. I have 2 central atoms. Each one of those carbons is central. This is a linear carbon, and this is a linear carbon. So overall, acetylene is just that straight line. Here in the top, I have, again, 2 electron groups on the central atoms, 0 lone pair, and that's where I get that linear geometry. Again, all of those molecules are in the same plane because they make a straight line. Here's a good exercise for actually looking at various ways that you can actually draw the Lewis structure, figure out what the geometry is, and then go ahead and look at the bond angles. So if you're going to look at something like this, let's look at this guy first, right? So again, I'm going to have the carbon attached to the carbon, and then the two hydrogens are going to go here. This hydrogen goes here. This goes there because I'm reading left to right again. So what I'm going to have is a hydrogen, and then I'm going to have some sort of a carbon with the three hydrogens. Now, whether I put this carbon up here or here does not matter. If I just flip it over, I'm going to see that it's the same molecule. What I do want to look at is this guy has 4 groups, 0 lone pair. So the electron geometry is going to equal the molecular geometry, which is going to be tetrahedral. My bond angle is going to be 109.5 because they're roughly the same size. This carbon up here might be a little bit larger, but nothing really substantial. This carbon is going to be 3 electron groups, 0 lone pair. This carbon is also going to be 3 electron groups, 0 lone pair. Got a tickle. So this is going to be the electron geometry is going to equal the molecular geometry because there are no lone pair. And this will be trigonal planar. There might be a little bit of a deviance from 120 degrees because this would be larger here relative to this one and vice versa. But we're going to go with approximately 120 degrees here, here, here. All of these trigonal planar bond angles are going to be basically 120 degrees. So what you have to do for these guys is you actually have to look at the geometry, and then you have to look at the bond angles. For example, this guy, let me just make another color. I'm going to read left to right again. I have this Lewis structure. And what I'm going to notice is this is going to be tetrahedral. This nitrogen is going to have an electron geometry of tetrahedral and a molecular geometry of trigonal pyramidal. So this bond angle between here and those two guys is going to be less than 109.5, probably around 107, like in ammonia. These guys are going to be 109.5. Those are just the regular tetrahedral angles. So you do want to take notice of what's around each central atom in case you want to sort of adjust your bond angle. Is it a little larger than ideal? Is it a little smaller than ideal? But for the most part, what you really want to characterize is that we have, what you really want to characterize is that, you know, my tetrahedral bond angles are about 109.5, my trigonal planars are about 120, and then my linear is about 180. So you do want to at least know those basic bond angles and then have a little bit of an assessment regarding if those are going to deviate or not based on comparative sizes. Now, let's quickly go to molecular polarity. Remember, we talked about bond polarity, but we have to look at the overall molecular polarity, which is going to be based on dipoles and geometry. So any molecule that contains a polar bond is nonpolar if the vector sum of its bonds dipoles is 0. So my bond dipoles are going to cancel out up with each other. For example, carbon dioxide, right? I have the bond dipole, right? That's pulling to, this is a more electronegative atom, right? But these are equal. Those two oxygens are equal. So this is going to pull in equal and opposite directions, which means they cancel. So my net result is 0, and this is going to be a nonpolar molecule. Each one of those bonds, each one of those carbon-oxygen bonds is in fact polar, but because I have a linear geometry and those bond dipoles are equal in magnitude because the two atoms are the same, but opposite in direction, they are going to cancel each other out, which gives me a net zero sum in terms of the dipole, which means this is going to be a non-polar molecule. Remember carbon tetrachloride? If you watched the mini lecture that I did on this topic in the review section, we talked about carbon tetrachloride. That was also a non-polar compound that has polar bonds. Now, in terms of water, right, I have two polar covalent bonds. Because it is a non-symmetrical geometry, because these dipoles, this is bent, right? So I have the blue vectors that go in this direction. If I add those together, I'm going to get this pink one that goes from the center. This whole area is partial positive, and this whole area is partial negative. As I can see, this is the partial negative part. All of this blue is partial positive. So the molecule has a charge distribution within its electron clouds. So I know that this is a polar molecule. Remember, if I have a polar bond and my molecular geometry is bent or trigonal planar, not trigonal planar, excuse me, if it's bent or trigonal pyramidal, it's going to be polar. If I have high degrees of symmetry with tetrahedral and linear and trigonal planar, then chances are, even if I have polar bonds, it's not going to be polar. And again, I talked about that before. Ammonia molecule, again, this is trigonal pyramidal. So even though I have all these individual dipoles sort of pointing up towards the more electronegative nitrogen, this is my resultant, and I get this whole area of this molecule is going to be the partial positive, and then this whole area of the molecule is going to be the partial negative. So the center of partial positive charge is actually midway between those three hydrogen atoms in the bottom of the base of that pyramid. Chloromethane, formaldehyde, those are going to be polar. Carbon-hydrogen bonds are non-polar. Carbon-chlorine bonds and carbon-oxygen bonds are polar. So I do have a permanent dipole here that's going towards the chlorine. So this is going to be partial negative. This is going to be partial positive. This is going to be partial negative. This is going to be partial positive because the oxygen is more electronegative than carbon. That's a polar bond, pulling the electron density of the molecule. You can see that here. This is partial negative. This is partial positive. This is partial negative. This is partial positive. Notice in this guy, I have symmetry. It's linear. Carbon-hydrogen and carbon-carbon bonds are both non-polar. So it's going to be a non-polar molecule. Now, one more topic that's really important is going to be hybridization. So let's look at the basics first. We're looking at shapes of atomic orbitals. We know s orbitals are going to have the shape of a sphere, and the center of the nucleus is going to be at the origin 0, 0, 0. A 1s is going to be smaller, a 2s is going to be larger, 3s is larger than the 2s, and so on and so forth. As I add more shells, those outer shells get farther and farther away from the nucleus, and they get higher and higher in energy. p orbitals consist of two lobes. I have a straight line along each axis. So I have three different p orbitals. I have one along the x-axis, one along the y-axis, and one along the z-axis. They do get sort of put one on top of another. So I end up with all of these different lobes. My p orbitals, each individual p orbital is 90 degrees away from any other p orbital, just like the coordinates, the axes in the coordinate plane. So just understand that this is when they're all three together, all of those sort of put on top of each other. Each individual one here is going to look like this dumbbell. Now, when I form a covalent bond, I have a portion of an atomic orbital of one atom overlapping and a portion of an atomic orbital of another atom. So if you watched my other mini lecture, we talked about forming H2, right? Because I have my one electron here and my one electron there. And then when they overlap, both those electrons form this covalent bond. And it's going to be nonpolar, linear, because I have two atoms or two areas of electron, or that actually I don't have a central atom, I just have that is going to make a straight line. So here's the problem though. When I overlap a 2s atomic orbital of one atom and a 2p atomic orbital of another atom, that's going to give me bond angles of about 90 degrees. Because remember, my S is spherical, and then I have the dumbbell shape, which are at 90 degrees. So I would get a 90-degree bond angle if that was going to go ahead and overlap. What we know is that I get tetrahedral geometries of 109.5. I get trigonal planar geometries of 120, and I get linear geometries of 180 degrees. In order to account for this observed bond angles in actual compounds that are measured experimentally, I have to use something called hybridization, which is actually a mixing of those s and those p orbitals. So sp3 hybridization is going to account for the tetrahedral geometry. sp2 will account for trigonal planar, and sp hybridization is going to account for those linear bond angles. And again, we're really focusing on carbon. So this is going to be single bonds, double bonds, and triple bonds when I talk, specifically about carbon. So if I look at the designation, right, sp3, I have one s and I have 3 of the p orbitals. That gives me 4, 3 plus 1, sp3 hybrid orbitals. sp2, I have 1 s atomic orbital. I have 2 p atomic orbitals. I get 3 hybrid orbitals. sp, I have 1 s. I have 1 p, that gives me 2 sp hybrid orbitals. Remember, this is tetrahedral, and I have 4 electron groups. I have 4 orbitals. This is trigonal planar. I have 3 electron groups. I have 3 orbitals. And this one is linear. I have 2 electron groups, and I have 2 sp orbitals. So this is all hopefully coming together in your head. Now, just to make things a little bit more complicated, because that's what we're all about in chemistry, haha, not really. Overlapping of hybrid orbitals can form two different types of covalent bonds, and this is dependent on the way that these orbitals will overlap. Sigma bonds are formed by direct overlap. So this is my head-to-head overlap. So this is where I have my orbital coming off of my atom and another one coming, and I sort of form a line along the internuclear axis, and I have those two orbitals sort of combining head-to-head. Pi bonds are parallel overlap. So these are my side-by-side p orbitals, right? If I have a p here and I have a p here, it's this overlap that's going to be above and below my internuclear axis, which is this, that is forming those pi bonds. So here's an example. I could have a P and an S, which forms a sigma bond. I could have a P and a P, which forms a PP sigma bond. I can have an sp3 and an S, which forms an sp3s bond. I could have an sp3 and an sp3 overlap, which forms an sp3 sigma bond. Because these are all overlapping orbitals, they're all head-to-head overlap. This forms, this is between the axis here along the internuclear axis in every case. These are going to be my sigma bonds. So sigma bonds. My pi bond is when I have the side-to-side overlap of my unhybridized p orbitals. So this would be a pi bond. My electrons are in that above and below. This is the internuclear axis right there. So I'm above and below that internuclear axis. My molecule, when I form a pi bond, is rigid, because if I do not have that side-by-side orientation, let's say I rotate this and these two orbitals here, right, these can no longer overlap because they are not in the appropriate space. So if I rotate the sigma bond between two carbons that have that pi bond, I'm actually breaking the pi bond because this can no longer overlap with this. Therefore, it's not a bond. And what I just did was break the bond. So the side-to-side overlap in pi bonds is less efficient than that for sigma. Pi bonds are weaker than sigma bonds. It's much easier to break a pi bond than it is to break a sigma bond. For pi bonds to exist, there must be a second bond that results in a double bond. So I have my sigma here, and then it's going to be the overlap of those p orbitals. This is my pi bond, and that is, again, I have my sigma here, I have my pi and the above and below, and this is going to be my double bond. So if this is a carbon and this is a carbon, I have my double bond. The first bond of any multibond is always a sigma bond. So my head-to-head overlap is always going to be there, and then that pi bond is and the head-to-head overlap is also in hybrid orbitals. My pi bond will always be formed between unhybridized p orbitals. So that's another thing that you have to know about this particular model. So any theory of bonding needs to explain why and how bonds form. And it also has to explain the observed molecular geometry. So this is an experimentally determined theory. What we were just talking about with in terms of hybridization models, that would be a valence bond type theory. This is pretty advanced, and in Chem 201, we do not worry about that. Valence bond, we worry about S, sp2, and sp3, because these are the hybridization schemes for carbon, right? Both of these use the idea of orbital overlap. This is a much more complicated treatment, so we don't have to worry about that. If you've taken Chem 121, General Chemistry 1, you have studied both of these basic bonding theories. If you've taken 100 or 101 or 110 in order to fulfill the prerequisite, you haven't had either of these. So it's a little bit harder at the beginning because you have to at least wrap your head around these guys and how they relate to carbon. You don't have to be an expert in these theories, but you do have to be able to distinguish between sp2 and sp3 hybridization. And again, that would be triple, double, and singly bonded carbon that we're really going to focus on. So remember, my bonds are created by orbital overlap, and that's going to produce sigma or pi bonds. When I think about this, in order to get those geometries, I have to combine the s and the p atomic orbitals, and then what I'm going to get is hybrid orbitals on atoms. These hybrid orbitals are going to form bonds between the atoms that produce the correct geometry. So remember, if I have one atomic orbital and one atomic orbital combining, I get two hybrid orbitals. If I have one s and one p, I get an sp. That results in a linear orientation. If I have one s orbital and two p orbitals, I get 3sp. 2 plus 1 is 3. That gives me trigonal planar. If I have 1s and 3 p orbitals combining, I get 4 hybrid orbitals, which are sp3. That gives me tetrahedral. So again, this is going to be the situation where I have 2 charge clouds. This is going to be the situation where I have 3 charge clouds. And then this is going to be the situation where I have 4 charge clouds. So again, this is what I have to know. I have to know how it all relates to carbon, because that's our most important element in this whole topic. So some other things. For a given atom, all hybrid orbitals have the same energy. The total number of hybrid orbitals that are formed is equal to the total number of atomic orbitals that are used to make them. Any unhybridized p orbitals can be used to do that side-by-side overlap and form pi bonds, or they can remain empty. And we'll see plenty of cases where those unhybridized p orbitals are there, but they actually don't have any electrons in them. So let's go through the carbon schemes of hybridization. When I look at carbon, and I'm looking at 4 equal atomic orbitals that has symmetrical geometry or has a tetrahedral Vesper shape, my atomic orbitals have to be equal in energy. Well, in order to get them equal in energy, remember, here's my valence electrons. Here's the 1s that I'm going to combine. I'm going to take the 1s and all 3 of the 2p's, and I'm going to hybridize. I get 4 hybrid orbitals, which is from the 1s plus the 3p's. That gives me 4 sp3. So I get 4 degenerate, which just means equal energy. My core is still down here. That doesn't change. Remember, it's the valence electrons that are involved in bonding. So this geometry, right, gives me these 4 degenerate sp3 orbitals. Now, here's an important thing. 1 out of the 4 is result in an S. It comes from an S, right? So I have an S, I have 3p, so I have 25% S character, 75% P character, because I have 1 S, I have 3 P's. If that totals 100, 1 out of 4 is 25%, 3 out of 4 is 75%. So I'm going to have more P character than S character, which is why this looks a little bit more like a P orbital. This is the carbon that is hybridized. Those sp3 orbitals form a tetrahedral shape. If I make methane, what I'm going to do is take the 1s orbital, and then I'm going to have the 2 sp3 orbitals in the second shell combining. I'm going to have spin pairing going on, and what I'm going to get is this tetrahedral methane with bond angles of 109.5. sp2, again, is trigonal planar. Consider ethylene, right? This is a trigonal planar carbon atom. This one is, and this one is. So each carbon must bond to 3 other atoms. So I only need 3 hybridized atomic orbitals. Here I'm going to combine the 2s and only 2 of the p's. This is going to stay unhybridized. This is what I'm going to use to make double bonds, which is right there, right? So when I hybridize, I have 3 lower energy degenerate sp2 orbitals, and I still have this unhybridized p. So when I put them together, this is what my sp2 hybridized carbon has. Here's my hybridization, right? This is 120-degree bond angles. And then here's my P, which is unhybridized, sticking up. This is all, these orbitals, if they're bonded to something, those are in the same plane. And then the P is above and below that plane, right? Now, 1 out of 3 is 33% S character. 2 out of 3, I have 67% P character. So this is going to look still a little bit more like a P, but it's going to be a little shorter, closer to the nucleus, because it has a little more spherical character to those as well. So this is how I'm going to form my sigma bond. This is going to be an sp2 orbital overlapping head to head with an sp2 orbital, right? So one of these electrons is from this carbon, the other is from this. That's going to be a head to head overlap. Something else can come out here, right? This is a sigma bond to hydrogen. This is a sigma bond. This is the sigma bond to hydrogen. This is another sigma bond to hydrogen. So this is going to be sp2 to the S on hydrogen. This is going to be sp2 to the S on hydrogen, right? This is going to be sp2 to the S on hydrogen. This is going to be sp2 to the S on hydrogen. Now here is where I'm going to get that side-to-side overlap. So when they combine, what I'm going to get is my pi bond. So if I look at how ethylene forms, right, remember what ethylene is. Here is my sigma bond, here is my double bond. And then I have the sigma bonds here, the sigma bonds here. And if I look at how all of those orbitals overlap, this is how it looks in terms of the orbital overlap on top of my ethylene. So this is sp2 hybridized. This is sp2 hybridized. It's trigonal planar. So my pi bond, again, is formed in the side-by-side overlap, right? The electron density of that pi bond is spread out above and below the plane of the molecule. These are different phases. The red next to the red is called in phase. We don't have to worry about that. You can worry about that later when you get into a higher level class. This is sort of the three-dimensional view. If all of these atoms, remember, trigonal planar, they're all in a plane, and then the P is sticking up and below that plane, right? This is where I'm going to get those pi bonds forming. These bonds are all sigma bonds that are from head-to-head overlap. So this is what it's going to look like. That's the pi bond just by itself. I have this head-to-head overlap. I have those electrons in that pi bond, and then I have this is actually sort of the molecular orbital treatment that we're not going to really worry about. I can also do this if I have oxygen, right? So if I look at oxygen, oxygen is also going to be sp2 hybridized, right? So what I'm going to see here is I'm going to have this oxygen, here's my sigma, and then my lone pair, this is an sp2, this is an sp2. Remember, that's also sort of trigonal planar because I have 3 electron clouds and I have a double bond. So this is the same hybridization. This oxygen is also sp2 hybridized. The sigma bond is the carbon sp2 to the oxygen sp2. The pi is going to be the p bond from the carbon to the p orbital from the oxygen. These other hydrogens are going to be sigma with the hydrogen S to the carbon sp2. This is going to be sigma from the hydrogen S to the carbon sp2. And then what I'm going to see is that my lone pair are also in these sp2s. Now, what do I really care about? Am I going to make you draw these? No. But if I have something that looks like this, and we know this is trigonal planar, we know this is also sp2 hybridization. So you do have to know that trigonal planar corresponds with sp2 hybridization. This valence bond theory actually is really easy to understand why this happens, but many of you are not at that level. But if you can start just looking at these diagrams, whether it's drawn out this way, which is a little more simplistic, or this three-dimensional way, if you keep looking at them and you keep thinking about them and maybe make a model of formaldehyde or make a model of ethylene or acetylene, and you can actually see a little bit more how these look like in three-dimensional shape. The last one is SP, right? This is going to be when I have linear geometries. So I want to think about this when I have a linear carbon. So this is going to be the carbon with 2 double bonds, 2 charge clouds, right? 2 electron groups, or a carbon that has a triple bond and a single bond. So this is acetylene. I have 2 carbon atoms. Both of these are going to be sp hybridized. This is linear on both carbons. And how I get that shape is here I'm only combining one of the S and one of the P's. I get 2 degenerate sp orbitals. Look at this though, I have 2 unhybridized p's. And this is my core, it's not involved in bonding. So this gives me, here's my hybrid. This is sp, this is sp. I get 2 hybrid orbitals. I have an unhybridized p above and below, another unhybridized p. So here, these p's are sort of 90 degrees to each other, and then the linear one, right? This is also 90 degrees to each one of those p's. This is the hybrid orbitals. This gives me linear geometry. When I put acetylene together, this is how I form that sigma bond. I'm going to have head-to-head overlap, and then this is going to form the pi bond. But this is also going to form another pi bond. So my triple bond is going to have a sigma and 2 pi bonds. This is going to be my sigma, this is going to be a pi, this is going to be a pi. So when you look at it, it's going to look like this, where I have the head-to-head overlap, which is the sigma, and then I have the pi, and I have the other pi. Those 2 pi's are 90 degrees away from each other. One goes up and down, one goes in and out of the plane if this is all in the plane. And again, this is a sigma bond, and then this sp to, this would be sp to hydrogen s. This is sp to hydrogen s. Those are where my sigma bonds, and then this is carbon sp to carbon sp. That gives me that original sigma bond. And then this pi bond is carbon p to carbon p. Let's call this the y direction. And then this would be carbon p to carbon p. Let's call this the z direction. And they are 90 degrees from one another. So this chart is what you have to know. You have to know this. You have to be able to determine whether this carbon is sp, sp2, sp3 hybridized, right? If I have 4 sigma bonds, I'm going to be sp3. That gives me tetrahedral. If I have 3 sigma bonds and 1 pi, that's going to be sp2. That's trigonal planar. If I have 2 sigma bonds and 2 pi, that's going to be sp, and that's going to be linear. So this is what you have to know out of all that treatment. It's easy if you understand the way the orbitals fit together, because then you understand and you don't have to memorize. It's harder if you haven't been exposed to this before. It may take a little bit longer. So the net thing is this chart is the chart that's really, really important in terms of knowing this material. Also remember, sp is 50% s, 50% p. There's only 2 orbitals, half of it's from an s orbital, half of it's from a p, right? sp2, I have 3 orbitals. 1 is from an s, 2 are from p, they combine, so it's 33s, 66p. sp3 has 25% s character, 75% p character. That's going to be important later on when we actually look at acidity and that kind of stuff. So here's sort of a summary. Here's my hybridization. Right? The steric number is just the number of electron groups. Anything that is tetrahedral in terms of electron geometry, right? I'm going to have these 3 molecular geometries, But notice that I can also, anytime I have 4 electron groups, it's going to be tetrahedral, which means it's going to be sp3. If my electron groups is 3, that's going to be sp2, trigonal planar. If I have 1 lone pair, that can be bent. If I have no lone pairs, that's going to be trigonal planar. If I have 2 electron groups, I'm going to have sp, that's linear. There's really nothing else I can do with that one. But remember, electron geometry is equal to molecular geometry if there is no lone pair. If there's a lone pair, my molecular geometry is going to be different. But what you want to be able to do is correlate these to carbon. So sp3 is a carbon with 4 single bonds. sp2 is a carbon with 2 single bonds and a double bond. sp is going to have 2 double bonds or a triple bond and a single bond. And that's the most important part of this entire hybridization scheme. So here's a question that you might talk about. So if I wanted to assign hybridization for all carbon atoms, I basically have to look at the VSEPR geometry, right? I have 3 hydrogens and 1 bond. So this has 4 electron groups, which is going to be tetrahedral, which is going to be sp3. This has 1 bond, right? This carbon has 3 electron groups. Trigonal planar, going to be sp2. This carbon, 2 electron groups. That's going to be linear for sp. Here, I have 3 electron groups. Trigonal planar, which is going to be sp2. Here I have 2 electron groups, which is linear, which is going to be sp. And then here I have 2 electron groups, also linear, which is also sp. So as long as you can sort of look at the structure, figure out the number of electron groups and correlate that to the shape in terms of the VSEPR shape, which is tetrahedral, trigonal planar, or linear, and then in turn correlate those shapes to the hybridization, you will be good to go for the rest of this class. And this is where we're going to stop this part. So there will be another 3rd lecture in chapter 1 where we focus on functional groups. So I will see you shortly in order to talk about functional groups, which will be the last part of chapter 1.